So we are now on the continuation of the application of the definite integral, still on the topic of work. And for this afternoon, we'll discuss Hooke's law and the spring work. So Hooke's law has something to do with the use, of course, of the Hooke's law constant, a formula that you have actually already encountered or was shared to you in your physics then. Now, Hooke's law states that the force required to compress a spring x units from its natural length, so whether it's either stretching the spring or compressing the spring, in which a corresponding change in its length is x unit, is proportional to x. That is, this force is f of x equal to the product of the Hooke's law constant k and the corresponding x, which is the change in the length of the spring. Okay, so the force needed to compress or stretch a spring to an x unit length change in length is equal to the product of kx. Give me a minute, class. So for example, is if a force of 1 Newton stretches a given spring 2 centimeters, so this is the corresponding change in the length of the spring, then a force of 5 Newton will stretch the spring 10 centimeters. Now, converting the distances to meters, we have the stretching of this spring 0.02 meters, requiring a force of the spring constant K and the corresponding change in the length, which is now in meters, which is 0.02. And from this, we can get, or we can solve for the spring constant, which is 10 divided by 0.02, which is 50 Newton meter. I think it will be best understood if I will show to you in terms of a computation, how is this done. Now, since the force, so I'll write here, since the force needed to change the length of your spring is equal to the product of the spring constant, the Hooke's law constant, and the x. In the discussion here in the next paragraph, you have here 5 newtons, which will stretch the spring a length of 10 centimeters. The force is 5 newtons, so this is the force. The change in the length is 10 centimeters, which is the x. Now, if you're going to change this 10 centimeters into meter, so what you're going to do, the x, which is the change in the length of the spring, will be divided by 100. And that would be equal to 0.10. So in this case, class, your F is 5 newtons and your X is 0.10. So determining the K would be a simple case of substituting 5 in here. You will have K as to be determined, the constant, and X, which is 0.10. So you will have K equal to 5 divided by 0.10, which is 50 Newton per meter. Now, why is this the unit? Because the 5 force here is Newton and this 0.10 is in meters from the original change in length, which is 10 centimeters. So this particular example here, or this particular second paragraph, is simply telling you how to determine the Hooke's law constant, or otherwise known as the spring constant, if given the force and the corresponding change in the length of the spring due to the application of the same force. Okay? Now, you may wonder, why do we need to find an equation for, or why do we need to find the Hooke's law constant or the spring constant? You need to find it because you need a formula. You need an equation that will represent your force. So if you know already that K is 50, from in here, we can say that your f of x, which will appear in the formula for the computation of the work, is equal to 50, your K, times the x. So when you determine now the spring work, I'd like to write this as W sub S. That would be the force times the displacement, right? So that would be then in this case, 50x, or rather, why did I place here x? Okay, 50x dx. Now, in here, you will have the corresponding change in the length of your spring. So, I place this blank, so your lower limit can be 0 and until here, depending on the corresponding change in the length. Let's say in this case, you want to know the spring work or the work done on the spring in stretching it to a difference in length of, let's say, 7 or 7, this is centimeters, so I'll convert it to meters, so that would be 0.07. Why do I need to convert the centimeters to meters? It's because my force here equation is in terms of Newton per meter. Okay, so that's the importance of finding the K, because you need an expression for the force and then you need to multiply it, of course, with the dx. In this case, it's not the displacement but the change in the length of the spring. Okay, now I think I have 2 examples here to discuss, that way your understanding for this particular application of the definite integral will be complete. But before I go to that, do you have any questions here? Okay, so there's none. So let me continue. The example 4, a force of 20 pounds stretches a spring from a natural length of 7 inches. This is the unstretched length to a length of 12 inches. How much work was performed in stretching the spring to this length? So you are to determine the work done on the spring to stretch it from 7 inches to 12 inches. Now, the force is 20 pounds. So, the force applied to stretch the spring is 20 pounds. Now, in many ways, we are not at all concerned with the actual length of the spring. So, we are not actually concerned with the 7 inches, only with the amount of its change. What is the change in the length of the spring? In this case, the change in the length of the spring, or we shall place it as delta x, is equal to 12 minus 7. So this is what we are interested in, the change in the length of the spring. Now, hence, we do not care that 20 pounds of force stretches the spring to the length of 12 inches, but rather that a force of 20 pounds stretches the spring by 5 inches. Okay? Now, this is illustrated in the figure below. We only measure the change in the spring's length, not the overall length of the spring. So this is the discussion. Now let me proceed to the next slide. So we are not yet able to determine the work done on the spring. So converting the units of length to feet, we have, so since our change in the length is in inches class, so it's in inches. And we know that if we're dealing with English units for the work problems, it should be pound foot and in foot. The length should be in feet or in foot. So in this case, we change the unit of 5 inches to feet. So you can see here the force needed to elongate the spring 5 inches. So it was divided by 12 to convert the inches into feet. So you have 5 over 12 times the K. Now, why is this like this? So I will write here, the force is equal to Kx based on the definition. Now, what is this particular x, the change in the length of the spring? That's the 5 inches divided by 12. So that is why you see 5 over 12 times the K. Now, why is it equated to 20 pounds? Because this force here is 20 pounds. The force that elongates the spring 5 inches is 20 pounds. Again, the purpose is to find the K. So in this case, your K is, so if you multiply your 20 by 12, that would be 240, divided by 5, that would be 48. So your K is 48. You can also check it from your end there. So 12 times 20 divided by 5 is 48. So your K being 48, you could see now that we go back to the original formula. F of x is equal to Kx. So K was replaced by 48. And then in terms of determining spring work, so we want to determine how much work is done in stretching the spring to a length of 5 inches. So it was converted to feet in here. And this one, the 48x is the F. And this is the corresponding change in the length of the spring. So the rest will just be your mathematics. Okay, your 48x when integrated becomes 24x squared, and you just substitute the limits 0 to 5 over 12. That way your answer will be in pound force foot, or foot pound force, since we are dealing with English units. So this is how we compute for spring work. It's still pretty much the same as the it's still actually based on the format of the formula for work, the standard format, that is force times the displacement. In here, nothing is displaced, only that the length of the spring was changed. Okay? Any questions? Okay, none. So let me clear my markings here. Yes, JB, yes, you're raising your hand.
Clarify, miss. So the 5/12, di ba, miss, is the length of the spring.
No, it's not
The I mean the wait.
the length of the spring. Okay, let me write para clear. The original length of the spring is uh,
Was it the change, miss?
let me go back to the
Okay,
problem.
miss.
Okay, let me go back to the problem. The original length of the spring is 7. The final length after this force was applied to it is 12, as you could see here. So the original length, for example, is 7. In here in the illustration, it's not 7, but it was just shown that there is a corresponding change in 5. So I'll write here on the next slide, so you would understand. The length of the spring original is 7. The final length is 12. Telling you that x is equal to 5. The change in the length of the spring. The force is 20. So if your formula is F equal to Kx, and you intend to find the K, you substitute 20 for the force, you still have K here, and the X will be 5. However, we convert it in feet, because if it's English, it should be in feet and pound force. That is why your K here is equal to 48. With your K equal to 48, you go back to this original formula for the force in terms of spring work. So your force now is equal to 48x. And this is the same expression of the force that will be placed in here in your integral. This is your force, and this is the displacement, et. Now, the displacement is not displacement here in the case of spring work, but the change in the length of the spring. Excuse me. Did you get it?
Yes, miss. Thank you.
Okay, I'm sorry about that, class. So you have any question here? The solution? Okay, if there's none, I will clear my markings here, and let's check if I have another example. Okay, so this work in pumping a fluid out of the top of the tank will be discussed on Thursday next week, because Tuesday is a holiday. Okay, Tuesday is a holiday, so we'll have it discussed on Thursday. Okay, hopefully I can continue with the other applications on work, which is pressure. Any more questions, class? If there's none, so I will just stop sharing.